Hi and Assalamualaikum and a very good afternoon. My name is Intan Adini binti Yahaya. My number is 88201694. Today I will present a study on how we can convert microalgae and marine plastic waste into cleaner bio-oil using a process called microwave catalytic co-pyrolysis. With the help of the smart catalyst derived from metal organic frameworks, we can explore a sustainable way to produce renewable energy from two types of waste, which is microalgae and marine plastic waste. Corella vulgaris, a type of microalgae, is known to produce oil that contains high level of nitrogen and oxygen. Unfortunately, this reduces the quality of the oil for use as fuel. On the other hand, marine plastic waste, which is a growing environmental problem, is rich in hydrogen and can serve as a hydrogen donor during pyrolysis. When we combine these two materials in a process called co-pyrolysis, we take advantage of their synergistic properties. The hydrogen from plastic help improve oil quality, while the reactive radicals from the algae accelerate decomposition. To further enhance this process, we use a bifunctional catalyst called ferrum oxide or C catalyst, which is we derive from metal organic frameworks or MOF. This catalyst not only improves microwave absorption but also promotes reaction like deoxygenation and denitrogenation. This method is a part of we call thermochemical conversion, where heat used to break down complex materials into simpler ones, in this case, into fuels. Microwave pyrolysis is especially efficient because it heats the material from the inside, not just the surface, making the reaction faster and more uniform. Our research had several key objectives. First, to turn algae and plastic waste into cleaner fuel. Second, to test how well the ferrum oxide or C catalyst improve the oil's quality. Third, to find the best mixed ratio of algae to plastic for high oil yield. And finally, of course, to reduce the nitrogen and oxygen content in the bio-oil, which is important for better combustion and storage. We were also addressing two global challenges at once, which is managing the increasing plastic pollution in oceans and finding alternatives to fossil fuels. By combining these two ways, we were not just solving problems, we were turning them into opportunities. We started by trying and grading Corella vulgaris and then preparing marine plastic waste by cutting and cleaning it thoroughly. The ferrum oxide or C catalyst, which was synthesized from metal organic frameworks, were added in different amounts, ranging from 10 to 30%. The co-pyrolysis was done using microwave heating at 800 watts. We tested different algae to plastic ratios from 100% algae to 100% plastic. We also measured the yields of oil, char, and gas. The oil quality was analyzed using GCMS, and we used SEM, BAT, and XRD to study the catalyst structure and performance. The preparation process was very important. We had to ensure the algae was properly dried and ground to ensure uniform heating, and the plastic was cleaned to avoid contamination that could affect oil quality. Ferrum oxide or C catalyst, our catalyst was derived from MOF because of their high surface area and tunable properties, making them excellent from catalytic reactions. Our best result came from the CAM2 ratio, which is 100% algae and 20% plastic. This ratio gave the highest oil yield at 29.4%. With the addition of the ferrum oxide or C catalyst, we observed better microwave absorption, improved heat distribution, and enhanced catalytic reaction. Reactions like aromatization, deoxygenation, and denitrogenation were all improved, which means the oil become cleaner and more energy dense. We also noticed that increasing the plastic content too much reduces the oil yield, possibly due to waxy nature of plastic residues. This suggests that a balanced mix or is crucial, and too much of either component can disrupt the synergy. The presence of the catalyst also increased the proportion of desirable aromatic hydrocarbons in the oil, which are important for energy applications.
To better understand the catalyst, we use SEM, BET, and XRD analysis. SEM, or scanning electron microscopy, showed the ferroxide or C catalyst had a rough and porous surface. This texture increases surface area, allowing more active sites for the reaction to occur. The BET analysis confirmed this, revealing a high surface area and pore volume, which supports better reactant diffusion and improved overall catalytic efficiency. Finally, XRD or X-ray diffraction confirmed the crystalline structure of ferrum oxide inside the carbon matrix. The clear diffraction peaks match well with standard ferrum oxide patterns, indicating the catalyst was well formed and thermally stable. Together, these results show that the catalyst is structurally suitable, chemically active, and physically stable for microwave pyrolysis.
The ferrum oxide or C catalyst plays a key role in making co-pyrolysis process more effective. Firstly, because it derives from metal organic frameworks, it has a high surface area and porous structure, which allows better contact between the feedstock and the active site. This improves the overall conversion efficiency. Secondly, ferrum oxide is magnetic and has excellent microwave absorbing properties. That means it helps heat the reaction mixture more evenly and rapidly, reducing energy loss and making the process more efficient. The carbon layer on the catalyst supports reaction like aromatization, wherein structured hydrocarbons form. This is important because these hydrocarbons are energy rich and suitable for use in transportation fuels. At the same time, the catalyst also promote the oxygenation and the nitrogenation reaction, and these reactions help remove oxygen and nitrogen containing compounds from the oil, which are responsible for pure stability, corrosion, and low combustion performance. We also notice a reduction in char formation, which is beneficial because excessive char reduces the overall oil yield and may block the reactor systems over the time. Less char means more efficient use of the original feedstock. In addition, the synergistic behavior of algae and plastic waste become more noticeable in the presence of the catalyst. The hydrogen-rich plastics donate hydrogen atoms, while radicals from algae help to crack large molecules into smaller, valuable hydrocarbons. For overall, the best results were achieved with the C8M2 ratio and 30% of ferrum oxide or C catalyst, which provided a good balance between high oil yield, low oxygen and nitrogen content, and a higher concentration of desirable fuel compounds. In conclusion, this study shows that microwave catalytic co-pyrolysis of Chlorella vulgaris and marine plastic waste under ferrum oxide or C catalyst is a promising method for bio-oil production. It increases yield, improves oil quality, and reduces nitrogen and oxygen compounds, making the oil more suitable for energy use. Is a clear demonstration of how waste materials can be transformed into value-added product using innovative technology. As the world looks for low-carbon energy sources, this method could offer a sustainable path forward. Because especially for coastal regions rich in biomass and plastic waste. This work also supports the idea of turning environmental waste into a renewable energy resources and contributes to building a more circular and green economy. I would like to thank all the institutions that supported this research for especially the National Natural Science Foundation of China and the South China University of Technology.
The details of this study are published in full journal, and the reference is provided here for further reading. So that's all from me. Thank you for watching.